Welcome to this demonstration of Agentic AI. I will showcase some of the capabilities of BigIP using Model Context Protocol, which is considered currently the most relevant protocol for Agentic AI. This demo is built using Red Hat OpenShift and its BigIP integration with F5 controller. Let's quickly introduce Model Context Protocol, or MCP for short, and Agentic AI. Let's first show the three main components. The arrangement is the typical AI application which makes queries to the AI model, but in this case, the AI application is MCP protocol enabled, which is the protocol used to talk with the AI agents. These AI agents are used by the AI model as well, but through the AI application. Let's see how this works. Step 1. On a startup, the AI application queries the agents which tools they provide. The agents return a list of the tools with a description and the parameters required. In step 2, when the AI application makes a request to the AI model, it includes the tools available. The AI, by reading the description of the tools and its parameter, is able to use these tools. Step 3. When the AI model finds out that it doesn't have built-in what it is required to fulfill the request, it makes use of the tools. The tools are accessed through the AI application. Finally, in step 4, the AI model composes a result with its local knowledge and the results from the tools it has used. Note from this picture that the AI application just needs to support the MCP protocol to use any tool. Without previous knowledge, the agent transparently makes the necessary transformations from MCP to the actual tool. This latter is very important because it means that we can extend AI models on the fly without requiring to rebuild the AI applications or even modify the AI models. Let's see this in practice. We are going to use LibreChat as the AI application, and we will use a locally served QN3 model using Ollama. We also enable two agents, a flight agent and a Formula One agent. And we are going to query the model, what is the closest airport to the circuit that hosted the first race of the F1 championship in the year 1970. You can see in the UI that two tools were called Get Race Calendar and Airport Search. And by using these two tools, the AI model was able to find out the answer to our question, in this case, the Grand Central Airport in Midrand, South Africa. If we click in the two calls, we can see the parameters used for the request and the responses obtained. Next, we are going to see the setup used to demonstrate some of BigIP's MCP functionalities. Using Red Hat OpenShift, we deploy the Ollama LLM server and two MCP agents for querying flights and Formula One related questions. In the other end, it is us using the LibreChat user interface, and in the middle, we have the F5 BigIP, which exposes the LLM server and MCP agents through two virtual servers, adding reliability, observability, and security. To configure the F5 BigIP, we make use of the Kubernetes API using F5 resources, which are ingested by the F5 sys controller, which updates the F5 BigIP when necessary. This F5 BigIP can be an appliance or a virtual appliance, even inside OpenShift virtualization. Let's see how this is configured in the BigIP using the Kubernetes API. In this case, we are using F5 virtual server CRDs. In the screen, we can see one for each MCP server, with different host names. To reduce IP address usage, these two virtual servers use the same IP address, also known as virtual hosting. Next, we can see how each virtual server is pointing to a different service in OpenShift. And last, we can also see that in addition to the Kubernetes readiness probes, it is also being checked the connectivity between the BigIP and the MCP server pods. For MCP workloads, it is necessary to have session persistence based on the MCP session ID. We will apply this and any other shared settings in a separated virtual server CRD, which will apply these shared settings for all MCP servers. Applying the configuration in the BigIP is done as usual in OpenShift. Let's wait until the configuration is fully applied. Now the configuration is ready. Even in this demo it is run a single client, Next, we are going to see the effect of removing persistence for the MCP protocol. Persistence is also known as session stickiness and guarantees that requests from the same MCP session always goes to the same MCP server. It can be seen in the logs of the AI application that the MCP server returns session errors because of the session mismatch. This ultimately produces a failure in the AI chat. A load balancer is a vantage point because it aggregates all the requests to all MCP servers, thus providing a unified and simplified way to log all this activity. Let's see how to do this. First of all, we can observe in the UI that the MCP virtual server incorporates the SSE and JSON profiles. These are needed to interpret the MCP protocol. These profiles also give us the capability to parse the MCP payload with iRules. We can send login messages with negligible overhead using BigIP's data plane high-speed logging facility. This also has great flexibility by allowing to incorporate custom information with the desired format for the receiving sync logger. In this case, we are showing an iRule that logs all the requests and responses, adding the IP address of the client, in this case, the LibreChat application. Using iRules, it is possible to inspect the details of the MCP messages and even modify them. We are going to show an example of this by controlling which tools are advertised by the MCP servers and also block requests from bad actors that want to use the non-advertised tools anyway. This blocking functionality is implemented in the MCP block tools iRule shown. The list of tools to be blocked is stored in a data group shown in the blue frame, which at the moment is empty. To see how it works, first we are going to see the initialization of an MCP server, and we are going to observe the initialization process by checking the high-speed login messages. We can observe the request in blue, the response in olive green, and in red, the MCP block tool functionality indicating that all tools have been allowed. If it is specified to block the tool airport search, it can be observed how the tool is blocked and no longer advertised to the AI application. This latter is shown in the blue frame. This tool blocking does not only occur in the tool advertisement phase, but also in case when a bad actor tries to use the disallowed tool. We can observe in the AI application this blocking in action. And with this, we finish this quick demonstration of Agentic AI with MCP and F5 BigIP providing reliability, observability, and security. We hope you have enjoyed it. Please reach to us for additional information on all the features available.